After completing this section, you will be able to define the Evolved Packet Core or EPC, the core network architecture of LTE. Define the Evolved UTRAN or UTRAN, the radio network architecture of LTE. Describe the S1 interface and the X2 interface. Explains different EPC components. Explain the functionality of LTE Uu Interface. The LTE network architecture, like any other mobile network, consists of three key components. User equipment called UE, access network which in LTE is called Evolved UMTS, terrestrial radio access network, UTRAN, packet core network, Evolved Packet Core, EPC. They work together to provide connectivity, mobility and services for mobiles. At a high level, the network is comprised of a core network, EPC, and the access network, UTRAN. While the core network consists of many logical nodes, the access network is made up of essentially just one node, the evolved node B, node B, which connects to the UEs. Each of these network elements is interconnected by means of interfaces that are standardized in order to allow multi-vendor interoperability. This gives network operators the possibility to source different network elements from different vendors. A departure from pre-4G architectures, the UTRAN is notably missing a controller. All of the radio access network functions are distributed to the cell site equipment, the evolved node B. The term LTE encompasses the evolution of the Universal Mobile Telecommunications System, UMTS, radio access through the evolved UTRAN, UTRAN. It is accompanied by an evolution of the non-radio aspects under the term System Architecture Evolution, SAE, which includes the Evolved Packet Core, EPC, network. Together LTE and SAE comprise the Evolved Packet System, EPS. EPC is a new, all-IP mobile core network for the LTE converged framework for packet-based real-time and non-real-time services. It is specified by 3GPP Release 8 standards. The EPC is a high-performance, high-capacity core network for LTE. EPC addresses LTE requirements to provide advanced real-time and media-rich services with enhanced quality of experience or QoE. EPC improves network performance by the separation of control and data planes and through a flattened IP architecture, which reduces the hierarchy between mobile data elements. For example, data connections from eNode B only traverse through EPC gateways. EPC is essential for end-to-end IP service delivery across LTE. As well, it is instrumental in allowing the introduction of new business models, such as partnering revenue sharing with third-party content and application providers. EPC promotes the introduction of new innovative services and the enablement of new applications. Introduction of EPC with LTE in many ways represents a radical departure from previous mobile paradigms. End-of-circuit switched voice, LTE uses a new paradigm for voice traffic VoIP. This ends a period of more than 20 years during which one application dictated the whole network architecture. EPC treats voice as it is, just one of many IP-based network applications. Evolved wireless broadband, LTE must match and exceed the QoE of wireline broadband. This is quite different from providing best-effort low-speed web browsing or short message service or SMS2 data applications for which the existing PS mobile cores were optimized. Mobility as a part of the core network, in LTE, all mobility management is moved into the mobile core and becomes the responsibility of the MME. This is a consequence of the split of functions previously performed by the RNC and Node B/BTS. End-to-end QoS becomes essential. LTE must provide superior end-to-end QoS management and enforcement in order to deliver new media-rich, low-latency and real-time services. There is an expected move from 4 classes of service or COS available in 3G to 9 QoS profiles with strict performance targets. This must be achieved while ensuring scalability of users, services and data sessions. Policy management and enforcement. In LTE, service control is provided via the Policy and Charging Rules function or PCRF. This is a big change from previous mobile systems, where service control was realized primarily through UE authentication by the network. PCRF dynamically controls and manages all data sessions and provides appropriate interfaces towards charging and billing systems, as well as enables new business models. The core network, called EPC and SAE, is responsible for the overall control of the UE and establishment of the bearers. Unlike 3G network architectures, LTE is significantly different in that it has no circuit core network for voice services. Voice services are established, like other IP packet data services, as Voice over IP, VoIP, typically using an IP multimedia subsystem, also called IMS, environment beyond the EPC. This greatly simplifies the architecture since voice is no longer handled as an exception case. Since the EPS only provides a bare path of a certain COS, control of multimedia applications such as VoIP is provided by the IP multimedia subsystem, IMS, which is considered to be outside the EPS itself. There are several functions provided by the EPC which include the management of mobiles within its domain, authentication of subscribers, and establishment of the bare paths to transport service traffic between the UE and a packet data network, PDN. These functions are supported by entities in the EPC like the Mobility Management Entity, MME, the Serving Gateway, SGW, the PDN Gateway, PGW, the Home Subscriber Server, HSS, and the Policy Control and Charging Rules function, PCRF. These entities are often combined into nodes according to the manufacturer's implementation. The Policy Control and Charging Rules function is responsible for policy control decision-making. The HSS is defined as the subscriber database for the LTE EPC, while the MME manages subscribers while they are in the network. The SGW and PGW are used explicitly for routing user traffic. The PGW is the mobile's IP address anchor and the gateway between a PDN and the LTE EPC. The SGW, in addition to being a router, is the local mobility anchor, so as a UE moves from one ENB to another, the bearer traffic will get switched at the SGW. The core network shares many traits with pre-4G network architectures. Something to be aware of is the separation of control plane, signaling, and user plane, traffic, in the core network architecture. This separation allows more flexibility in implementation and independent scalability of the control and user data functions. Some of the main functions of the EPC are establishment and enforcement of quality of service, COS, for user services, and allowing a mobile UE to maintain a consistent IP address while moving. The EPC is designed to interwork with legacy wireless networks. The air interface is located between the UE and the ENB. The air interface is called Uu Interface. This interface uses orthogonal frequency division multiple access (OFDMA) and single carrier frequency division multiple access (SCFDMA) and OFDMA variant on the downlink and uplink respectively. OFDMA is very spectrally efficient and allows for the use of multiple antenna techniques like multiple input multiple output (MIMO). The evolved UTRAN consists only of cell sites, or evolved node B, ENB. In addition to providing radio functions, the eNode B performs some key control functions including scheduling of the airlink resources or radio resource management, active mode mobility or handover, and admission control for services. The eNode B is also responsible for selecting which MME will serve the UE, and for protocol features like header compression and encryption. Elimination of a central controller, for example, a radio network controller, by distributing its functions to the eNode B simplifies the network architecture and potentially reduces packet delays. The eNode B that make up an UTRAN can collaborate with one another for radio resource management and handover. The inner eNode B communication is referenced in standards as X2. Inter-cell communications using the X2 interface between the eNode B is new and unique to LTE. Similarly, the reference for UE to eNode B communications known as the LTE Uu and UTRAN to EPC communications is designated as S1. The S1 interface is separated by control plane signaling and user plane traffic. The variant of S1 used for control plane signaling is referred to as S1 MME, and for the user plane as S1U. The primary function of the ENB is radio resource management. This includes scheduling of both uplink and downlink air interface resources for UEs, control of bare resources, and admission control. The ENB, as an agent for the EPC, is also responsible for the transfer of paging messages which are used to locate mobiles when they are idle. Finally, the ENB performs other critical functions including communicating common control channel information over the air, header compression, encryption and decryption of the user data sent over the air, and establishing and over-reporting and triggering criteria. As mentioned earlier, ENBs collaborate with each other over the X2 interface for functions like handover and interference management. Now that we have studied the high-level LTE architecture, let us now focus on the key functionalities of different nodes within EPC. Let us start with Mobility Management Entity, MME. A mobile's MME is selected by the ENB from which the mobile initiates system access. From functionality perspective, the Mobility Management Entity manages user equipment, UE, within the LTE EPC. As such, the MME manages subscriber authentication, maintains a context for authenticated user equipments, establishes data bearer paths in the network for user traffic, and keeps track of the location of idle mobiles which have not detached from the network. For idle UEs that need to be reconnected to the access network to receive downstream data, the MME will initiate paging to locate the UE and re-establish the bearer paths to and through the UTRAN. In the establishment of the user's data bearer paths, the MME is responsible for selecting the PDN Gateway, PGW, and the Serving Gateway, SGW, which will make up the ends of the data path through the EPC. The Serving Gateway, SGW, functions primarily as an IP packet data router. From a network architecture perspective, the SGW is the UE's bearer path anchor in the EPC. As the UE moves from one node B to another during mobility operations, the SGW remains the same and the bearer path towards the UTRAN is switched to talk to the new ENB serving the UE. If the UE moves to the domain of another SGW, the MME is responsible for transferring all of the UE bearer paths to the new SGW. Within the EPC, the SGW, acting upon direction from the MME, establishes bearer paths for the UE to one or more PDN gateways, PGW. SGW also retains the information about the bearers when the UE is in the idle state, and should downstream data be received for an idle UE, the SGW will buffer the downstream packets and request the MME to locate and re-establish the bearer paths to and through the UTRAN. In addition, the SGW performs some administrative functions in the visited network, such as collecting information for charging, for example, the volume of data sent to or received from the user, and lawful interception. The PDN Gateway, PGW, is the gateway between the LTE network and a packet data network, PDN. While the PGW functions primarily as a router for user traffic, there are some significant functions the PGW performs on behalf of the UE. These functions include IP address allocation for the UE, packet filtering of downstream user traffic to ensure it is placed on the appropriate bearer path, enforcement of downstream quality of service, QoS, including the data rate. The PGW performs QoS enforcement for guaranteed bit rate, GBR, bearers. PGW also serves as a mobility anchor for interworking with non-3GPP technologies such as CDMA 2000 and WiMAX registered networks. Depending upon the services a subscriber is using, there may be multiple user data bearer paths between the UE and a PGW. It is also possible that the subscriber is using services on PDN served by different PGWs. In this case, the UE will have at least one bearer path established to each PGW. During handover of the UE from one ENB to another, if the SGW is also changing, the bearer path from the PGW is switched to the new SGW. The home subscriber server contains users' SAE subscription data such as the EPS subscribe QoS profile and any access restrictions for roaming. It also holds information about the PDNs to which the user can connect. This could be in the form of an access point name, APN, which is a label according to DNS naming conventions describing the access point to the PDN, or PDN address, indicating subscribed IP address. In addition, the HSS holds dynamic information such as the identity of the MME to which the user is currently attached or registered. The HSS may also integrate the Authentication Center, AUC, which generates the vectors for authentication and security keys. The Policy Control and Charging Rules function is responsible for policy control decision-making, as well as for controlling the flow-based charging functionalities in the Policy Control Enforcement Function, PCRF, which resides in the PGW. The PCRF provides the COAS authorization that decides how a certain data flow will be treated in the PCRF and ensures that this is in accordance with the user's subscription profile. The ENB and the EPC have a many-to-many relationship to support load sharing and redundancy among MME and SGW. The ENB selects an MME from a group of MMEs so the load can be shared by multiple MME to avoid congestion. LTE does not support soft handover as there is no centralized data combining function in the network. The LTE Uu Interface, referred to in LTE standards as the LTE Uu Interface, handles all signaling between the UE and the network. It carries all signaling messages between the ENB and the MME, as well as all user traffic between the ENB and the SGW. Both the control plane and user plane of the Uu interface are supported by the same set of interface functions like security and header compression, and are all carried by the physical layer over the air. The physical layer in LTE is based upon orthogonal frequency division multiplexing, OFDM, using orthogonal frequency division multiple access, OFDMA, in the downlink, and a variant of this called single carrier frequency division multiple access, SCFDMA, in the uplink. There are several functions which support signaling and traffic on the air interface. These include security, like message authentication and encryption, IP header compression, data protection with encoding and retransmission, UE synchronization with the LTE physical layer, broadcast of system information. The signaling carried on this interface will support functions like connection management, handover and paging. This completes the module. Click next topic from navigation menu.